Hello again. In this our session, we are going to use the programming language environment R in order to calculate the expected value of functions of conceptual random variables. Now, you see in the theoretical course, we have seen how to calculate the expected value variance and the distribution of discrete and continuous random variables respectively. Therefore, in our first practice, we are going to learn how to calculate the expected value of a function of a discrete random variable, such as the binomial random variable. And in the second application, we are going to learn how to calculate the expected value of a function of a continuous random variable, such as the normal random variable. So let's start with our first practice. The question says that our random variable capital X is a binomial random variable with size parameter 200 and success probability 0.85. So you see here we have a binomial random variable with a moderately large size parameter. Therefore, if we intend to calculate the related probabilities, it will be a little hard for us. But unfortunately, the success probability is not very small. In fact, it is also large. Therefore, it is not a good idea to approximate this binomial random variable with a Poisson random variable to ease the calculation operations. Fortunately, we have the programming language environment. Therefore, it is just going to help us to calculate the probabilities. And here in this question, it says that there is a function g of x, which is defined in three parts. For x values which are less than or equal to 50, it is simply equal to 1. For x values which are between 50 and 100, 50 is not included, however 100 is included, it is x minus 50. And for x values which are greater than 100, it is x to the power 6 over 5. So this is a little complicated function, and it is partially defined. Therefore, when it asks us to calculate the expected value of a g of or random variable, it is not a very good idea to make these calculations using manual methods. Therefore, we are just going to use the programming language to define this function, and then we are going to calculate the expected value of the function of this random variable. So this is our theoretical function. The first thing that we need to do is to write this function down. So let's do that. So remember, our function is equal to 1 if the input value is less than or equal to 50. So we are just going to say that g is a function of the input variable x, and within the curly brackets here, we are going to define what g does. So we know that it is equal to 1 when x is less than or equal to 50. It is equal to x minus 50 if x is greater than 50, and so it writes lowercase x, but it should also be less than or equal to 100, so that this function is going to be valid. And otherwise, if x is greater than 100, then it is equal to x to the power 6 over 5, and this is going to be valid when, of course, x is greater than 100. This function is defined like this, and we are interested in calculating the expected value of g of capital X, a function of a random variable where x is binomially distributed with size parameter equal to 200 and success probability equal to 0.85. So what we are going to do is this. We know that this random variable, binomial random variable, can take integer values from 0 to 200. So all possible integers from 0 to 200 are theoretically possible for this random variable in its realization. Therefore, what we are going to do is we are going to calculate the probabilities for each binomial realization, and we are also going to calculate the g of this value, the function of this value, and we are going to take a weighted average of those. So my input values are changing from 0 to 200 as integers, and the expected value of g of x is what? It is equal to the summation of the response values in g for all integers from 0 to 200, and we are going to multiply these values respectively with the probability mass value in binomial distribution with size parameter 200 and success probability 185. And the result will be the expected value of g of x, which is 474.881. So this is how we do it. This is how we calculate the expected value of a function of a binomial random variable. Now, what I have done, let me show it again. I have selected everything with Control A. These command lines are selected with Control A, and I press Control R to run these functions in the console. Now, the next application is the same practice, but this time for a continuous random variable. Therefore, instead of running a weighted sum of the function values of discrete realizations, this time we are going to use the integral approach because our random variable will be continuous. Now, in this example, the random variable that we consider is a normal random variable with location parameter 50, and it says variance 4, which means the standard deviation or the scale parameter or the sigma value is equal to 2. Now, my objective is to calculate the expected value of the maximum of two values. So it is just going to calculate x minus 55. Now you see this normal random variable is going to be distributed around 50. So the possible realizations are going to be observed around 50 with standard deviation 2. So it is just going to take too many values around 50 with a normal distribution. Now, for every realization, our objective is to calculate this maximum function. We are just going to subtract 55 from the realization of this random variable. If that value is positive, then we will take that value. However, if that value is negative, then we will take 0, because we are comparing this value with 0 and taking the maximum of these two values. So it can either be 0, the response of the function can either be 0, but if the realization is greater than 55, then it is going to be equal to x minus 55. So our objective is to calculate the expected value of this function, the expected value of the maximum of x minus 55 and 0. Now, this value can be calculated through this integral. So if we are interested in calculating the expected value of this function, where the input is a normal random variable, we need to integrate that function multiplied with the normal density with location parameter 50 and scale parameter 2. And we are going to integrate this integrand from minus infinity to infinity theoretically, because a normal random variable can take all possible real values in theory. However, since we are going to calculate this integral using a programming language, we can get huge numerical errors when we use the integrate function between minus infinity and plus infinity. Even though the function is going to converge to 0 in these two tails, we can still get numerical errors. Therefore, we need to write down logical boundaries for this integral. Now, what we know is for standard deviation 2 and location parameter 50, when the values are 10 sigmas, or 10 standard deviations far from the location parameter, the probability density function is just going to converge to 0. In fact, we have stated that in the theoretical course, even when you move more than 4 standard deviations far from the location parameter, the PDF values are just going to be very, very small. Therefore, if we are going to calculate the integral, this integral, it is just sufficient to integrate it between 10 standard deviations away from the location parameter, and we are going to get the same result. So what we are going to do is this, again, just like in the previous practice, we are going to define the function g here. Now, what was that? The g function, it's a function of x. It is just going to compare x minus 55 with 0. If x minus 55 is greater than 0, then we will take that value. Otherwise, we will take 0. So remember, such comparisons can be made by using the Pmax function. So whatever the input value x is, okay, whatever the Pmax input value x is, this is just going to compare that value with 0, and if that value x minus 55 with 0, and if x minus 55 is greater than 0, it will take this value, otherwise it will take 0. In fact, let's try this. Let's try this for example, 57.5, 56, and 54. Okay, so what we know is if this function is correctly coded, then the responses will be respectively 2.5, 1, and 0, of course. So that function is coded correctly. Now, the integrand, which is the input of the integral, the input function of the integral is called integrand. The integrand of consideration is what? It's the product of g of x multiplied with the probability density function of the normal distribution, which we know. However, remember the location parameter is 50, the scale parameter is 2, and the expected value of the function of this random variable will be calculated by integrating this integrand function. However, remember, if we want to integrate this between minus inf and plus inf, so this is how we write it. Now, if you check that value, you will get a 0 simply because of the numerical error. Because if you want to calculate this integral in the extreme tail, such as infinity, even though the density function gets so small, we can still get numerical errors. Therefore, we need to be very careful if we do not want to get a numerical error. Remember, what we have said is we are just going to integrate this function between 10 scale parameters away from the location parameter. Okay, so that is between 30 and 70 for this example. Okay, now if you do that, and if you check the expected value, now the expected value is 0.004, okay, and the absolute error is so small. So this is basically how we are going to do it. So expected value here is very small. Okay. So I think there is a mistake in the PDF file. In the PDF file, it says 1.2978. So I'm just going to check if this is true or not. Now, if you integrate this integrand between 30 and 70, you are going to get this value. And if you do that between 20 and 80, I think this is true. This is correct. So the mistake is made in the document. Maybe we need to change the document here. And basically, this is going to be all. All right. So we have learned how to use a programming language to calculate the functions of conceptual random variables. Whatever the function is, we need to write that function in the form of a vectoral function, which can calculate the function for several values at the same time, just like in this example. Then you can easily use R to calculate the function of expected value of a function of a random variable. In fact, you can also calculate the variance of a function of the random variable as well. All right, so I'm just going to stop recording now.